Good afternoon, everyone. I'm Erlens. I'm going to talk about Appstract, which is a privacy-respecting system we built that understands the semantics of contents people consume in their apps. This is joint work with Oriana and Suman at Microsoft Research. So we are interested in the semantics of contents people consume as they interact with these apps because this can enable lots of new experiences. So say, for example, here I'm listening to some music. A system that understands this fact will know that I am listening to Shockwave Supernova, and armed with this information, it can provide these intelligent cards with options to, say, view the lyrics of this album or even purchase this album. Now, these functions are not natively supported in this application. And you can actually use such technology today. Google Now on Tap and Bing Snap are some examples of this emerging technology. As entity extraction is the core technology that enables all of these features. And simply put, it is simply extracting all of the text you see on the screen, and it is associating semantics with that text. So for example, here, I'm assigning the semantics or the entity album to the raw text, Shockwave Supernova. Similarly, I'm assigning the entity artist to the raw text, Joe Satriani. And here are some other examples of other entities, for example, restaurants, addresses, and cuisines. So now just with extracting these entity types, you can have a lot of interesting features. So say that a user always selects vegetarian restaurants, vegetarian recipes in a recipe app. A system that understands entity types will be able to mine historical preference and essentially automatically reorganize a list of cooking books when that user searches simply for cooking books on Amazon, for example. As another quick example of the power of entity type extraction, say that Alice is booking a trip to New York. She will obviously search for some flights, maybe book a hotel, and then search for some restaurants. Now, a system that understands these entity types will be able to extract all of this relevant information from these screens directly and create a trip itinerary automatically, as opposed to Alice manually copying all of this information into a document, for example. So this is very exciting technology. It has a lot of potential. But in today's climate, it is natural to ask, what about user privacy? I mean, after all, this technology is seeing everything you are seeing in your app, and it is associating semantics to that information. Well, such systems essentially transmit all of the data you see in your apps to their cloud backends to do this entity extraction because it is a compute-intensive process. Now, this might be OK for some apps, but for certain apps that manage privacy-sensitive information, like this drug management app, or your banking app, this might not be so OK. And these emerging systems actually recognize that there is a potential for privacy breaches here, and they have some privacy control mechanisms. So we studied Now on Tap as an example. And Now on Tap has this interesting feature where developers can disable extraction for pages they deem sensitive. So we decided to study and see how used this feature is. And we did a measurement of top 1,000 apps, including several privacy-sensitive categories. And unfortunately, we found that only 70% of financial apps and 2% of medical apps actually have some of their, have entity extraction disabled for some of their sensitive pages. Therefore, we conclude that these developers are leaving users to their own devices to control their own privacy, and this is not a very good idea. Therefore, we come to the central question we're trying to address with this work here is, like, obviously, can we do this entity extraction locally, keep all the data on the device, and hence providing better privacy? Well, the answer is yes, you can, but there are a few challenges that we recognize and we overcame in this work. So first is that these systems have very poor, like mobile apps have very poor context. So context is simply the set of words that surround any given word the word which you're trying to associate semantics to. So for example, in this screenshot here, you can see that the text is highly structured, but there are very few words surrounding the text. So they just mention the name of the restaurant, for example. And so web-based systems generally have a lot of context because you have a lot of text surrounding any given text, but on mobile apps, you have poor context. We went further and we tried to run existing tools to see whether we can overcome this. So we ran the Stanford named entity recognizer tool, which is a state-of-the-art entity recognition algorithm, and on this mobile app data. And unfortunately, we found that the accuracy or the F1 score is only 41%. Existing state-of-the-art systems on the web have an accuracy of at least 80%. And the reason for this big gap in accuracy is essentially this lack of context. And the second challenge is that the cloud-based systems run resource-heavy algorithms on their cloud infrastructure. Particularly, they have very large knowledge bases, which makes them unsuitable to run directly on the smartphone. So we built Appstract, a system that overcomes all of these challenges, and it essentially extracts entities accurately and efficiently without sending user data to the cloud. So very quickly, let's say that on OpenSpoon, I want to basically extract entities from this page. The first thing Appstract is going to do is it's going to extract all of the contents on the screen. Now, since mobile apps structure all of their data in UI trees, which are similar to HTML DOM trees, we are going to extract a UI tree. And importantly, we're just going to leave this on the device. And then we will extract entities from this tree using a process that we call template matching, and using this data structure that we introduced called the entity template. So the entity template is another UI tree. It shares the same structure as the target UI tree, but its nodes are annotated with entity type codes. So in this instance, the matching process is essentially going to let me infer that Jade Dragon is a restaurant. And these entity templates can encode other information on other entity types also. So here we have like addresses and cuisines. So these entity templates sound magical, right? I mean, they're solving all of our problems. Well, I mean, it's not really magic. It's actually possible. And it's possible due to two primary observations on the structure of UI in these mobile apps. So the first is that many UI elements contain single entities. So we studied the top 25 apps from various categories, and we found that like 70% of the UI elements have less than 6 words. And this essentially implies that we can go and annotate a single node of the tree as a particular entity type. The second observation is that these apps have few but stable UI structures. So again, we studied the top 14,000 apps, and we found that 80% of apps have less than 26 types of pages. So this essentially means that we can extract all of the entity types from the apps only by generating a small set of stable templates. So then the obvious question is, can we generate these templates automatically, accurately, and most importantly, user agnostically? So we built an offline entity extraction pipeline that computes these templates in a user agnostic manner. So the first step is to use an application crawler or a UI automation tool to execute these apps automatically and extract a lot of UI trees for a lot of apps. And then we pass this to a KB-only extraction phase that uses 3 feature vectors, along with some knowledge bases to produce UI trees. But these UI trees are now annotated with probability vectors for each of the text-bearing nodes. So the probability vectors essentially give you the probability of the corresponding text as being a particular type of entity. So by convention, let's say P0 is the probability that this is some entity type that we do not recognize. P1 is a probability this is a restaurant. P2 is a cuisine, and so on. And so we generate these probabilities using these knowledge bases. And the knowledge bases are small, and they simply contain enumerations of entity types. So for example, a restaurant knowledge base will contain like names of restaurants like Nara and Cardamom. And at this point, it should be immediately apparent that these knowledge bases are fundamentally incomplete. You cannot enumerate everything that is in the world. And so this is going to produce low probabilities. And couple that with the fact that we have very little context, and essentially this will produce very low probabilities and not allow us to extract entities very accurately. So we built several analysis techniques that exploit regularity in UI trees to boost our probabilities and minimize the effect of this lack of context. So the first is called cross-page patterns. And this essentially tries to use multiple instances of pages to overcome the lack of data in the knowledge base. So say that I do not have data about the Spanish restaurant in my knowledge base, but I may have data about the Japanese restaurant, and that will help me offset the effect of that lack of information. So we built an algorithm that looks for repetitions across page structures. And essentially, the output of this step is, again, a UI tree annotated with probability vectors that are combined across instances. And then we go one step further, and we look for regularity within a single page. So in this list-like object, we see several patterns like repetitions of restaurant, cuisine address, restaurant, cuisine address. So our goal here is to use this kind of regularity to further boost the probabilities that we are calculating. And this is challenging because we are finding a repeating sequence, a repetition in an uncertain sequence. And so we built an algorithm that essentially traverses the tree, and at each node it evaluates several entity assignments and essentially assigns entities based on the maximal probability at that level. And so at the end of all of this, we produce our entity templates that are UI trees annotated with entity types. We send this down to the device where we, at runtime, we match the extracted UI trees and we extract entity type codes. And interesting to, the main takeaway from this slide is that this is all user agnostic. It got nothing to do with any user. So here is a quick demo of this entity extraction working on the device. So the user is just going to play with some restaurant app, and you can see the system dumping these entities in real time to the log. And all of this is happening without any specific user's data. This is user agnostic. Okay. So we built this system. As I said, it's called Appstract. We built it for Android and Windows Phone. The Android version, notably, is just simply an app. You can just install it on your phone. Based on this Appstract system, we built 5 use cases for Android and 3 use cases for Windows Phone. For example, we built this ranked list UI element that automatically reorganizes its contents based on the user's preference in a particular entity type. So if I like rock music, it's going to give me rock music before all other kinds of news. We also built this contextual menu example that essentially detects the kinds of entities highlighted on the screen and then presents an automatic shortcut. In this case, it's going to save that restaurant's data to the contracts database. So finally, in terms of evaluation, we looked at Appstract from several perspectives, but just to summarize very quickly here, it is fast and it does not consume a lot of energy on the device because at runtime, we are just simply matching these UI trees. We are not doing any kind of cloud communication. To generate the templates, it takes a couple of minutes, and the template sizes are approximately a few hundred kilobytes. Please see the paper for details on those parts of the evaluation. I'm going to focus on the most important part here, the template accuracy. So we manually generated these ground truth templates for 17 apps, and this involved manually annotating hundreds of UI elements with their entity type codes. And then we computed 3 numbers. The first is the precision, or in other words, what portion of the generated template actually matches the ground truth. And our baseline approach is simply the knowledge base system, and Appstract is all of the techniques that leverage regularity. And we see that on average, Appstract outperforms the KB-only approach, primarily due to the regularity analysis. Similarly, we computed the recall, or in other words, how much of ground truth did we recover? And here again, we see the regularity helping us overcome that lack of knowledge and lack of context. And finally, the F1 score, which is just a harmonic mean of precision and recall, this is like approximately 80%, and this is actually comparable to existing state-of-the-art web-based entity recognizers. So in summary, understanding the semantics of these contents in apps is very powerful. It can enable a lot of experiences. But the problem is the way systems are architected today, they send all of this data to cloud backends. What we show with Appstract essentially is that you can extract entity types in a privacy-respecting manner without sending all of this data to the cloud. And you can do it accurately with a very good F1 score that is comparable to existing systems. And we also showed how you could use Appstract to build to recreate many existing use cases like contextual menus and ranked lists. Thank you.